Welcome to The Explainer. Today, we are taking a deep dive into the absolutely incredible physics and engineering behind one of the most talked about technologies in modern defense, hypersonic missiles.
So let's just jump right into it. What does it actually take to fly at 20 times the speed of sound? This isn't just a matter of strapping a bigger engine on something. We're talking about surviving physics so extreme that they're literally reshaping global defense strategy as we speak. In this explainer, we're going to break down the 5 monumental engineering challenges that have to be solved. We'll kick things off with what Mach 5 really means, then get into the wall of heat, the wild propulsion problem, the challenge of flying completely blind, and finally, why this all makes interception just so incredibly difficult.
All right, first things first. Before we go any further, we really need to get on the same page about what Mach 5 and beyond actually means, because this is, and I mean this literally, a totally new realm of flight.
So what is hypersonic flight? Well, on paper, it's pretty simple. Any speed over Mach 5. But the real key here is that this isn't just faster supersonic flight. This is the exact point where the very chemistry and physics of the air around the vehicle start to change. The air itself stops behaving like, well, air.
To put that into perspective for you, a pretty typical re-entry speed for something like an ICBM warhead is around Mach 20. That's nearly 6,000 meters per second. At that speed, you're not just flying through the atmosphere anymore. You are in an all-out fight with it every single moment.
And that fight brings us to what is pretty much the single most dominant engineering challenge of hypersonic flight, surviving a literal wall of fire.
Just get a load of this number. At Mach 25, the stagnation point, that's the very tip of the vehicle, can hit temperatures of 18,000 Kelvin. That is hotter than the surface of the sun. There is no material known to man that can just sit there and take that kind of heat without being completely vaporized.
Now here's where the physics gets really interesting. The heat doesn't just go up in a straight line with speed. Oh no, it scales with velocity cubed. That means if you double your speed, say from Mach 4 to Mach 8, the heat load doesn't just double, it multiplies by 8. It's an exponential nightmare for the engineers.
So obviously you can't just build this thing out of steel. The materials science has to evolve right alongside the speed. You might start with advanced titanium alloys around Mach 5, but by the time you're pushing Mach 25, you're forced to use extreme ablatives. These are materials that are actually designed to burn away in a controlled way, carrying all that destructive heat away with them.
And this right here is one of the most counterintuitive solutions in all of aerodynamics. You'd think for going super fast, you'd want a needle-sharp nose, right? Nope. Turns out for hypersonics, you actually want a blunter leading edge. What this does is it pushes the main shockwave and that super intense pocket of plasma and heat slightly away from the vehicle's skin. It creates this tiny buffer that can mean the difference between flying and just disintegrating.
Okay, so you've solved the heat problem. Your vehicle isn't a puddle of molten metal. Fantastic. Now, how in the world do you actually power it? This is what I like to call the engine for a hurricane problem.
So engineers have basically come up with 2 main ways to do this. On one side, you have boost glide vehicles. The idea here is to use a huge rocket to shoot a glider way up to the edge of space, get it going crazy fast, Mach 15, Mach 20, and then it just separates and sails unpowered all the way to its target. On the other side, you have air-breathing vehicles, which use this incredible engine called a scramjet to fly inside the atmosphere.
Let's just take a second to appreciate the scramjet. It's an absolute marvel of engineering with basically no major moving parts. It uses the vehicle's own insane speed to ram air into the front, compress it, squirt some fuel in, ignite it, and then the hot gas expands at the back for thrust. And the whole thing happens while the air is still moving at supersonic speeds inside the engine. It's just mind-boggling.
And this number right here perfectly illustrates the central challenge of a scramjet. At Mach 6, the air you need to mix with fuel and burn is only inside the engine's combustor for about 1 millisecond. The analogy you always hear is perfect. It's like trying to light a match in a hurricane and expecting it to stay lit. It is one of the most extreme environments humans have ever tried to control. All right, you're surviving the heat. Your engine is somehow miraculously working. But just as you solve one problem, a totally new one pops up. You are now flying completely blind, trapped inside a plasma bubble of your own making.
They call it the plasma blackout problem. That same intense heat we talked about earlier is so powerful, it actually strips electrons from the air molecules around the vehicle. This creates a sheaf of ionized gas, plasma. And this plasma sheath, it's like a brick wall for radio waves. GPS, communications from the ground, remote commands, none of it can get through. You are completely, utterly cut off. So how do you get around that? Well, you have to get pretty clever. You can try trailing a long antenna behind the vehicle in its wake where the plasma is a bit thinner. You could even try using powerful magnetic fields to create a kind of window. But more often than not, you have to rely on a super sophisticated internal guidance system and pre-programmed maneuvers. Basically, you have to tell the missile exactly where it needs to go before it enters the blackout.
And that reliance on internal guidance demands almost unbelievable precision. With GPS gone, the missile is just coasting using its own internal gyroscopes and accelerometers. And these numbers show you just how razor-thin the margins for error are. A tiny, minuscule drift of just 1/100th of a degree per hour can cause you to miss your target by 100 meters after only 10 minutes of flying blind.
And this all brings us to our final and most critical point. Why does solving all these insane physics problems actually matter? Well, it all comes down to the interception challenge.
So what makes these weapons such a nightmare to stop? It really comes down to three things. First, they fly low, way under the radar of the big space-based sensors that are designed to spot high-arcing ballistic missiles. Second, they can maneuver. They can jink and weave and change their target. And third, just their sheer, raw speed crushes a defender's reaction time.
And this chart right here puts the problem into stark perspective. For a classic ICBM, a defender might have about a 10-minute window to try and intercept it. But for a hypersonic glide vehicle, because it's flying lower, that window shrinks to maybe 2 minutes. And for a low-flying hypersonic cruise missile, you are looking at less than 1 minute from the moment you detect it to the moment of impact. There is almost zero time to react.
And let's say you do manage to launch an interceptor in that tiny window. You're still facing this number. The closing speeds are so enormous that to hit a target that's making even a slight maneuver, your interceptor has to pull between 50 and 200 Gs in the final half-second of flight. That is pushing the absolute structural limits of any technology we have today.
So the huge takeaway here is that hypersonic weapons aren't just faster missiles. By solving these incredible challenges in materials and propulsion and guidance, they are fundamentally changing the basic math of time, distance, and defense. And it leaves us with one final, very profound question. As the physics that used to be theory turns into operational reality, how do we adapt to a world where the uninterceptable is no longer just a concept?